next presenter will be Cristiano Flati, and he will be presenting IPv6 transition mechanism.
Thank you very much. Nice slides. I hope this time they work. So I'm going to split my presentation in. First, I'm going to. I will try to explain why, or try to reach a common agreement on why IPv6 is the only way for the future. So we can understand why all this hard work that is required on network providers is the best way for the future of the internet. We usually say that we are not going to replace one protocol with the other. It's not going to be a migration. It's going to be a transition. There's going to be coexistence of both protocols for some time. And all of us, when we connect to the internet, we just want the service. We don't care much about what are the details in the protocols underneath. So all of us are going to have more devices, devices at homes and devices we are going to carry, phones, tablets, notebooks. All of them are going to have its own IP address, and all of them will need end-to-end connectivity. So all of them will have to, some way, connect to the rest of the internet. That we don't want to have subsets of the internet. We want each of them to have the same experience that we currently have with our regular connections. And as we know, there are no more IPv4 addresses available. So there must be a way to have an equivalent service with something else. So, as I said, in the current internet, we are using IPv4. It's an IPv4 network, the internet as we know it. And these IPv4 addresses run out or are running out, so we need to extend the amount of addressable devices with IPv6, but there's no way to replace one with the other on a single day. When the internet started, like actually it started like 40 years ago, but 30 years ago there was a switch on the protocol that was used, and as there were a few devices connected to the internet, they were able to make this replacement in a single day, to switch one protocol with another one. With IPv4. So when the internet started using IPv4, this change was done in a single day. But now it's not a possibility. There's no way to migrate a network and to replace one protocol with the other. So there's going to be a coexistence or a transition. There's going to be a slow deployment of IPv6, so we are going to see this curve of traffic growing slowly in the future. And IPv6 hosts are going to be there for a long time. So this coexistence period is going to take several years. So there must be techniques to make both hosts interact or coexist. So why are we doing these IPv6 day activities, and why we started doing them? Well, the techniques that are used for this migration, or actually not migration, but this for this coexistence, were not working properly enough. So there wasn't enough interest on several providers to deploy IPv6 because there were several issues with the service when they started doing IPv6, especially for content providers. Content providers were claiming that if the content was configured on IPv6, their customers, some of the customer, a percentage of them, would not be able to reach them. So there was no disincentive. There was not enough attention or not enough interest to configure IPv6 on content networks because of these problems that could arise. And these problems are due to the transition techniques that I'm going to explain in the next slides. So what we tried in the beginning in 2011 was to do in a single day a test, mostly for content providers, to try IPv6. And that was World IPv6 Day in 2011. And with this test, they were able to verify that the users were not having that much issues as they thought. So this year in 2012, we did what it's called World IPv6 launch and several activities, like this activity here, trying to accelerate the IPv6 deployment. So it's not just convincing people that the protocol is not going to introduce any issues on the service, but also trying to encourage the network service providers to start using it not anymore as a test, but as a commercial service, because there's no way for them to keep growing. The most efficient or most business rational decision would be to start thinking about deploying IPv6 instead of trying to keep using or growing based on IPv4 addresses. So because of all these issues on the transition, this IPv6 deployment has been like a moving target, and content providers were not willing to configure it, and service providers were not providing IPv6 service to their users because there was not content available. So this hopefully have changed during the World IPv6 activities, and nowadays we are all on the same page, I would say. So now let's go to the specifics on IPv6 transition or IPv6 coexistence. And this is mostly focused on service providers, which are the ones with the most work to do, I would say. These slides are based on a workshop that we usually do with the CTLD in Brazil. So these are slides that are used for training network people in our region. So as I said, we are currently using IPv6, the IPv4, so there's no way to switch. So let's see how can we make both worlds work at the same time. There are several techniques that service providers can do to deploy IPv6 while their network is still using IPv4. And first, the first techniques that I'm going to explain are based on tunnels. These are techniques that encapsulate the IPv6 packets on IPv4 packets, because the current networks are able to understand the headers of IPv4 packets. So when we try to connect two IPv6 hosts, routers, or whatever, we add an additional IPv4 header and then we send them to the network. We'll see some techniques in the next slides. Then we've got translation techniques that tries to make something similar to a NAT, but with taking care of the differences of both protocols and some of the tools that are required, because it's not just mapping addresses. There are more things to be done there and some complexities. Then I'm going to say something about CGNs and what if they keep using IPv4 addresses, doing network address translation again on their networks for the private addresses that are being used by their customers. And then what I would say is the most recommended solution, that is deploying both protocols on the network and try to build their service based on that. So tunnels. They are also called encapsulation, because this is what we are doing. We are adding an additional header. Imagine if you've got your current IPv4 network working properly and you want some customers to have IPv6 service, then what you do, if if you are getting IPv6 service from your upstream provider, you just configure a tunnel from the router that is providing service to your new customer, the one that is requiring IPv6, and this tunnel is going to end on one of your routers that can have IPv6 service from your provider. This is why we call it encapsulation of tunneling. There are other tunneling techniques that I'm going to explain that are more based or more addressed for individuals or that are configured automatically. But on my previous case, that was a provider that willing to provide IPv6 services to their customers without an IPv6 network, then in those cases, the IPv6 service can be received from tunnel brokers. These are IPv6 service providers that have equipment that is ready to finish these IPv4 tunnels that are going to be encapsulating IPv6 traffic. So we can configure a tunnel from your router or host to one of these tunnel brokers, and from there you are able to reach the entire IPv6 internet. You have to register yourself in one of these tunnel broker service providers and configure something manually on your devices, either a router or a host. And as soon as you finish your configuration, you are going to have IPv6 service available. It's a very easy configuration in most of the cases, either routers or hosts. But it's not recommended as a long-term solution, because this is usually done when you want to test something on IPv6. It's very fast to enable IPv6 using this technique, but it's not scalable. You're not going to be able to deploy one of these solutions on a big network. So let's go to the next proposal or solution that is available, and that it is how to configure routers. So there is a technique, or there are some techniques, 624 or Teredo, that will let end users or devices to automatically create a tunnel to a relay and encapsulating the IPv6 packet in IPv6 packets until they reach the relay, and then they will be sent to the IPv6 internet. So the IPv6 address for those automatic configurations are going to be based on a specific prefix. This is the prefix, and within the IPv6 address is going to be the current public IPv4 address. So the IPv6 address that you are going to use when you use 624, it's based on a specific prefix plus your current IPv4 address. This is how the IPv4 packets are going to return to your device before they are this additional IPv4 header for the packet is removed and sent to your IPv6 device. In order to reach one of these devices that are going to make this encapsulation, these relays, there is a specific IPv4 address. These public relays are going to use this IPv4 address that is there, 192.88.99.1, and there are several of them on the internet. So as soon as you send an IPv4 packet with this IP address, it's going to reach the closest 624 relay, and it's going to traffic or it's going to do this trick of removing the IPv4 header that is used to encapsulate IPv6 traffic, and it's going to send it to the IPv6 internet. So everything is done automatically. There's no need to configure anything. Just enable 624, and the magic, it's magically they're going to reach the IPv6 internet. The problem with that, there are several problems, and we really don't encourage ISPs to deploy 624. But one of them is that the traffic is not going to be symmetric. The packets initially are going to go from an IPv6 client to the 624 relay. In this case, they're going to be on an IPv6 network to to a router that is channeling the traffic to the 624 relay, the one with the IP address that I mentioned, 192.88.99.1. So it's going to be encapsulated in this part. So from here to here, it's going to be IPv6 within an IPv4 packet. So the packets are going to be IPv4, and when they reach this relay, they will get then as soon as this IPv6 is ready, they are sent to the IPv6 network, they will reach the server, but when these packets are sent back to the original host, so we get the reply from the server, then they are not going to reach the same relay, because they are going to be sent to the IP address that was created automatically based on the prefix I mentioned, plus the IPv4 address, and they are sent again to the closest IPv6 relay 624 on the network. So from the server perspective, the closest relay is not going to be the same as when the packet was coming. So they will go through a different relay. And this can introduce some problems, especially when things are going wrong and we want to make some diagnosis. This asymmetric routing is usually complicate things for diagnosis. So in order to prevent these problems, the providers can install their own 624 relays in their networks. What are the general problems with these 624 techniques? Well, first of all, it requires a public IPv4 address in order to work, because, as I mentioned, this was going to be used to create the IPv6 address, because it's needed in order to reach back the IPv4 connected device. When we send a packet, we've got a public IP address, which is 1234. This should be included in the IPv6 header, because when the traffic returns, it's going to use this public IP address to get back to my 624 router. So there's a need for IPv4 public addresses in order for this to work. The relays are going to encapsulate the traffic without much verification on what's within. And this introduces some problems and the possibility of IP address spoofing. We can create valid packets, tunneled packets, that are going to be encapsulated or decapsulated on the relay and sent to the client, and there's no way for this relay to tell if they are legitimate or not. And also there's no authentication between the 624 routers or devices and the relay. So there are some security concerns on this technique. As I said, one of the operational problems is that the providers that are using, or the networks that are using this technique, have to use relays that are not under their administration, because they send to this general address and someone else is probably taking care of this relay. Well, if network providers do have 624 traffic, they can deploy their own 624 relays in their networks. And in some cases, they can reduce these problems. But there is an even better solution, which would be to deploy a similar technique, but not using the same prefix, the same 624 prefix that makes this asymmetric routing, because all of the 624 devices are going to use the same prefix. If the service provider use their own 624 prefix, this is a similar technique that it's called 6RD, and this traffic will go through their relays and not through the public relays. So I said that one of the issues is that you've got to use public IPv4 addresses in order to make 624 or 640 work. So a solution or a workaround for that is Teredo, which is another automatic tunneling technique. It's mostly used on Windows operating on Windows devices. It's the same thing, except that this is going to be first encapsulated in UDP, and this UDP traffic will go through NATs and through devices in your local network. So there's no need it can go through these NAT devices. And how is it done? Well, it's similar to 624, but first, in order to know what is going to be the public IP address, it has to connect to a server, to a Teredo server that is going to assist the client on what is its public IP address. Because when you are on a local network, you are using a private IP address, and you got no idea what is going to be the public address when you send packets. So you have to trust on a Teredo server that it's going to help you, the client on getting what is going to be the public IP address in order to create similar tunnels. And there are also different sort of NATs. So it's not just querying a Teredo server for what is his IP address, but also trying to detect what kind of network address translation is configured in the network. So there's a lot of overhead on the initial connections in Teredo, because it has to detect what is the current NAT within the network, what is the public IP address, and then the packets are sent, and the initial packets will go through one path, and then the Teredo client should connect to the Teredo relay to create like another path, and then traffic will go through this second relay for the remaining traffic. All these negotiations take some time, and you can notice that as a user. When you're using Teredo, you can notice this additional delay when using IPv6. There are still some concerns with Teredo, and the traffic, as I said, it's encapsulated in UDP traffic instead of being IP in IP. It's a UDP header there, and this will go through firewalls, and there's no way for these firewalls, or currently the firewalls will not pay attention to what's encapsulated within this UDP. So we will have the IPv6 traffic encapsulated in UDP and then IPv4. So the firewall is just going to see regular UDP traffic, but inside there's going to be a different IPv6 header with an additional IPv6 payload. So there are some security concerns because, as Carlos said, many people trust on NAT as a secure mechanism for everything, and in those cases, most of the traffic are going to go through the NAT without any filtering at all. It's going to be, even if there's a firewall available, then it will go through the firewall as regular UDP traffic. Also, there is a concern because the Teredo client is going to announce what ports are used and what type of NAT is available within this local network. So you are exposing your network details to a server that is not configured by you or managed by you. And if there's a denial of service attack to one of the relays, and it's the same case with, it's the same thing with 624, if there's a denial of service attack to one of the relays, all of the customers that are using this relay are going to be affected, and could be thousands of customers. And if you're an attacker, in both cases you can install fake relays, so you can receive this encapsulated traffic and do whatever you want with it. So the last tunneling or encapsulation technique would be GRE, which is a generic technique to encapsulate any protocol in IPv4. And this is usually done when you've got a network and certain portion of the network is not IPv6 ready, or it's difficult to deploy IPv6 in certain parts of the network. Then you can create these channels to bypass. So you have to configure both ends of the tunnel on your network, and all the traffic will go through this tunnel, but it requires manual configuration on both ends. This is also usually the case when your service provider does not provide native or dual stack IPv6 services, but they've got a router in their network with IPv6 service. Then they usually let you configure your cherry tunnel to connect to this router in their network, and from there you've got regular IPv6 service. Of course, as all the encapsulating techniques, there's some more overhead because additional headers are included, but it works pretty well. So this is the example I mentioned. You got a IPv4 part on your network, that it's only IPv4, it's not going to understand IPv6 packets. So what you do, you manually configure GRE in a couple of routers to create this manual channel, and traffic will go through this channel on this portion of the net. So MPLS. Carlos mentioned that it was very easy on BGP because of VPNs to add V6 services on MPLS networks. How many of you are currently using or are aware of MPLS? Anyone? 1, 2, 3, 4. Okay. So those service providers that are currently using MPLS on their networks, there is a very, very simple technique to have native V6 on your edge routers. The edge routers, the routers that are connecting customers on the MPLS networks, are called PE routers, provider edge. So you have to configure a few things only on those PE devices, on those that you would like IPv6 enabled, and that's it. Because all the packets are going to be forwarded based on labels within the network. So it's just to add the appropriate labels for IPv6 traffic to reach the PEs on the other end that are going to get to the IPv6 destination, and that's it. There's no performance impact, there are no scalability issues. It's going to grow on your network as your current MPLS network grows. There are no additional features to enable. It's very, very simple to configure. And there's no need for those networks to deploy in the entire network. They go and select specific PEs, specific routers on their network, on their edge, that they are where they want IPv6 enabled. Well, as I said, the forwarding of the packet is similar to what it's done for VPNs. On those networks, there are like multiple IP networks sharing the same IP routers, and this IPv6 traffic is going to be just an additional VPN. It's going to be very, very similar as an additional VPN. I'm going to go through this faster. Then we've got, as if we remember, we have the tunneling techniques. Then we have the translation techniques, which will try to map one header to the other instead of adding an additional header. So we will have devices that will try to adapt the IPv4 or IPv6 header in order to reach the other party. This is regarded when you've got one end with only IPv6 and one end with only IPv4. So in general, they will all use what is called SIIT which are some recommendations when mapping IPv4 to IPv6 or vice versa. They usually don't need to make any additional changes on the inner protocols. They're not going to map anything on UDP or TCP. And they also need some additional considerations on ICMP. So there are going to be specific transformations for ICMP packet. But they usually need some help, because it's not like with NAT that you just map one header to another or one address to another. There are some additional services that needs to be adapted in order for these techniques to work. Like, for example, DNS. When you've got an IPv6 only client that is willing to connect to IPv4 only client, he's going to send a DNS request with a quad A. As if you remember yesterday, if the client wants an IPv4 address, it asks for a single A. If it wants an IPv6 address, it asks for a quad A. So it's going to send a quad A, but the server should recognize this query and will realize that the device that he's trying to connect is only going to have an IPv4 address. So this DNS server is going to answer with a fake or a transform IPv6 response with an IPv6 address that is going to be understood by a device that is going to make the header transformations. In this case, we are in an IPv6 only network that is trying to reach an IPv4 only device. So both equipment, the DNS server and the one doing the translation, should be aware of these connections. There are several problems on these techniques that requires the traffic to go through a device that is doing the header transformations, and also the complexity on the DNS part, because they've got to work in tandem. We are requiring that all the traffic should go to a single device, which creates a single point of failure and some scalability issues. And there are some additional concerns regarding as I said before, for an attacker it's a very attractive target for denial of service. But they're going to be used very often when we start seeing IPv6 networks or access customers that require connections to IPv4. So compared to other techniques, these are not going to be the worst. What would be a real problem is when the providers, instead of growing with IPv6, when there are not more IPv4 addresses, they try to keep using private IPv4 addresses, what we call CGNs. So we have the home networks with IPv4 using the current NAT that we've got at home on our broadband devices, for example. And these are going to be translating to, and again, private IPv4 addresses that are private within the ISP network. And those packets are again will go through a NAT device for shared IPv4 specs. So we've got at least 2 network address translations for all the traffic we send. This, of course, it's going to introduce several complexities on the operation, and these boxes are going to be extremely expensive because all the traffic should go through them, and the scalability issues will require that these providers are going to be spending more and more money growing these devices when their service grows. So I would say that this is probably the most expensive solution, and it's also introducing several complexities on the operation and diagnosis of the service. So what would be the recommendation? Well, all of the previous techniques were transition techniques. There were techniques that are required when you want to keep both when you want to keep the IPv6 hosts with IPv6 only connectivity and the rich IPv6 4 hosts that only have IPv6 only connectivity. But it's possible for all the devices in the network to have both protocols configured. And it's the best solution until we run out completely of IPv4 addresses. So as long as we do have IPv4, public IPv4 addresses, that will be the best way to go, because there will be no need for additional translations. And when we run out completely of addresses, then the translation is going to be easier, because it's going to be just for the IPv4 traffic to reach IPv4 only devices that hopefully are going to be less and less in the future. So what we do basically is to add both protocols to the operating system, and depending on the DNS answer, packets are going to be sent using IPv4 or using IPv6. And again, the decision on which protocol to use, if both ends have both protocols available, it's going to be based on other for example, on performance. If you've got a dual stack machine that is going to connect to Google, for example, and Google has both IPv4 and IPv6 enabled, then your browser can decide which one to use based on previous queries and performance. It's a proposal in the IETF that it's called Happy Eyeballs, and that can adapt on which one to use when both are available. And if not, well, it's very easy for the application. They will use the only one that's available, and traffic will go easily without any interference in the middle. So deploying dual stack requires changes in the entire network. That is probably, it's not yet the most widely deployed IPv6 service on all the service providers' network. And requires changes and configurations on the DNS servers, on the routing protocols, on all the firewalls, in network management, in several places. It's probably the one that impacts most on the network, but it's also the best way to go. So for those of you considering transition techniques, my recommendation would be try to make all the work, planning it in advance, doing it slowly, but the deployment in the entire network using dual stack, instead of going through one of the other techniques that looks fine but are going to complicate your operation. So thank you, and I'm open to questions.
So Christian,
Yes.
this isn't a question, it's just an observation. I was a vice chair of the U.S. Federal IPv6 Task Force. That meant that I worked in government to try and help government networks transition. And the technology that Christian was talking about was carrier-grade NAT. That makes law enforcement very, it complicates life for law enforcement. The director mentioned the other day working with law enforcement for different issues that come up. We currently are working through I know some law enforcement officials are working through the IETF and others to try and help with solutions
Yes, and when you start doing or going through this solution, then you're going to keep spending money all the time while you are growing on your business. So you are introducing something that is going to be a new source of expenses on your network, and it's not going to end because the network will go to IPv6 instead of to IPv4. That's why it's going to keep growing. So, yes.
If I understand it correctly, then there are two approaches that we should look at. One of them is customer facing from the edge, and the other one is the core approach. And so basically the dual stack is something you suggest from the edge towards the customer, and perhaps something like 6PE for the core initially until you're ready to go forward.
Yes, in those cases where the MPLS network is currently already deployed, going 6PE would be the easiest way because it only needs changes on the edge and towards the customer equipment.
So we'll stack towards the customer and 6PE in the core.
Yes, which is also dual stack somehow.
Yeah.
Because if you've got an MPLS network, you are not using anymore the IP header to route traffic. You are going to use a label.
Oh, exactly, but you still have the control plane that's still running IPv4, right?
Yeah. So we can consider it as dual stack as well. But yes, if you already have MPLS, that would be the best approach. Yeah.
From a cost perspective, I just want to give a little idea of what it would take to actually run carrier grade NAT. It's something that we thought about, but the thought only went through our minds for a minute after we looked at the cost. It will cost you $250,000 per router.
I actually thought my voice was much louder than that. So most service providers in the Caribbean use two vendors, primarily either Cisco or Juniper. On a Juniper box, it would cost you, Chris, you can keep me honest here, about $250,000 to get the correct modules to run the carrier grade NAT. And on Cisco, I think the minimum device you would have to use is an ESR 9000, which is a pretty expensive device. So to do carrier grade NAT, you need to do some forklift load in your network. So the dual stack only sometimes cost a version upgrade. Yeah, just wanted to give you my thoughts on it.
Thank you. Okay, no more questions, so let's proceed. Thank you.